So let's get started on this course. I'm excited to be teaching this course. So my name is Hamid Behmanesh. Two of my colleagues, Shri and Felix, will be helping me with the question and answer. We are expecting over 100 plus participants, so hopefully more people show up. And we'll be happy to walk you through what we have for the fluid material balance as a part of one of the modules that we have in Whitson Plus. Let me get started with my laser pointer as well. Okay, let's move ahead. So let's start with some meeting logistics. As I said, we are expecting more people to show up, and seems to be people are showing up as we go into 8. 8 and we are expecting for 3 hours of course for fluid material balance. And if you have any question, please reach out to the chat box. And we're gonna have a couple of breaks in the middle of the course, so we can have a conversation during those times and also after the class if there is any question that you would like to deep dive into them. And Whitson Plus, so we're gonna use Whitson Plus modules of Whitson software as a web-based application. Hopefully, most of you guys are familiar with the software. So there are many different modules in the software, DCA and TIFO, PVT, bottom hole pressure, fluid material balance, which is the focus of this course today, and numerical and analytical RTA. For today's course, we're going to combine these fluid material balance modules with different modules that we also have. And one of them is the full physics reservoir simulation. So we are going to show you how we can combine different modules that we have here. And the output from fluid material balance, which is one of them is average reservoir pressure, go directly into the nodal analysis. So these modules that we have here, somehow they are not independent. The result from one should be complementary to the result from others. And I'm going to show you how you may utilize different modules that exist in the Whitson Plus. There's another component to this. This is Whitson PVT. It's fundamentally focused on characterizing the reservoir fluid. So if you want to learn more about this, please reach out to our support team. And a couple of events is happening later in October. One of them is VidCon, is the annual conference that we invite legends from the industry to present their learnings and their findings and their analysis and experience on actual field data. Basically most of them are using Whitson Plus software. So it's encouraging to be part of this event as well. So it will be happening October 2nd. And throughout the year, we have many different courses. So far, we have gone through 3 of them, PVT and bottom hole pressure and analytical numerical RTA. Today, we are going through fluid material balance. There's more schedule. I missed one of them, which is happening on September 25th, which is focusing on fundamentally numerical simulation and the capability of numerical simulation modules that we have in Whitson. So if you are interested, please reach out, and also this information will be disseminated through our weekly email that Jessica is sending out. So if you want to be part of those email lists, please let us know. It's highly recommended to get to know the different functionality, because dynamically everything changing. We are dynamically changing a lot of features every day. So, and most of them are reflected in our certificate. The number of certificates is starting to grow. Recently, we have added one numerical certificate and PNR decline. So it's encouraging, and I highly recommend, not for the sake of earning a certificate, but mostly you get to know what are the features. What are the features that you may not be aware of on the daily basis. So it gives you some hints that you can also do this with this feature. So it's recommended to earn the certificate, not for the sake of the certificate, but also mainly for the realizing what are the most recent features, because this certificate constantly get updating. So it's worth as a refresher to take a look at them as well. Great support team. Some of you might have experienced this in the past, that try to get to your ticket regardless of any ticket from any company. in as soon as possible. Usually, it is the first minute that you send out an email, you receive multiple emails, and oh, we are taking a look at that. Depending on the complexity of the case, some of them are very easy to address. So we're gonna get back to you as soon as possible. Some of them require some the developments under the hood, so take a little bit longer. But I guess everybody, if you have been working with Whitson and experienced that support, you concur it is amazing. So in terms of the software, okay, well, what we're going to be covering today. So by the end of today, we will be covering multi-phase flowing material balance, but it's not limited there. Try to cover how it is connected to different modules and different components in Whitson. We show you how to log in and access what will be the industry standard workflow in terms of getting in the data, looking at the data, and analyzing the data, and getting some meaningful results out of the data. That's the workflow that we're going to walk through, and what's the structure and functionality of the software. And it's fundamentally based on the FMB. There's two components to this flow material balance. First is the flow material balance with the estimate of what's the contacted oil in place, how much volume we have drained, and the complementary part of the flowing material balance is to get the recovery factor. So if we got the recovery factor and the original oil in place, we can calculate EUR. And we're going to do some comparison between EUR that we estimate from flowing material balance and others like numerical simulation, a simple material balance, or also PNR decline. So that's the intent of the course. And so you guys should be able to access the software platform. So what I'm gonna do right now, I want you to please go to whitson.courses.com. So this is the whitson.course.com, and you should be able to see FMB course 2025. So please go ahead and check this out, course.whitson.com and FMB course 2025. And the credential for logging is the email that you registered with. So if you're affiliated with a company, please don't use your company name, company email. Use the email that you register for the course. And the password is Whitson FMB 2025. So if you can access these, then you should be able to see FMB course here. And if you have any problem with accessing these, please send us a note in the chat or contact us as soon as possible so we can grant access to you. Once you are here, then click on the FMB course and you should see this one. Some of you already, I'm glad to see some of you already created your project. So go to project, add project on the top and click on add project and make the project known so it is unique to you. So I'm gonna make it my project initials and save the project, and now it is on my now I'm in my project. So one more time in the FMB course, add the project and name the project to be unique to you. This should be showing up here. Your name should show up here. So 29 of you apparently have done that so far. I encourage everyone to please do that because we're gonna do a lot of examples here, and the example FMB project. So this gentleman maybe make it a private one. So if it is private, you will be the only one that will be able to see your project. But if it is company wide, everybody in the list will be able to see that. So once you do that, means that you guys have access to the software. Okay, we're gonna go ahead and so in terms of the workflow, which is this is the slide is prepared for the unconventionals with the intent of modeling multi-frac horizontal wall, but but some of these modules are not unique to unconventional. So the PVT and fluid characterization is the first step that because all of these properties we're gonna show up in bottom hole pressure calculation, volumetric numerical simulation. So that's the first step to get it right, PVT and fluid characterization. And it's very easy step. Depending on how much information that you have, you can import those information into the software and make it more characterized to your reservoir fluid. But there are very easy way to also characterize your fluid based on the producing VOR. I'm going to show you that. The next step is the bottom hole pressure calculation for the FMB that we're going to talk in today. FMB is also requires bottom hole pressure calculation. Sometimes we calculate from the surface using the PVT and wellbore information. Sometimes we have gauge data, so we're going to utilize those gauge data for calculating the FMB, for instance, in this case. Next one is the multi-phase FMB. So multi-phase FMB, despite the fact that it's a unconventional reservoir workflow, but it is basically wellbore geometry agnostic. It doesn't depend if you're draining from a tight reservoir, if or a Darcy, Milli-Darcy type reservoir. So either conventional or unconventional in terms of the flow behavior and volumetric. So that's something that will apply to all the fluid that we might have. Okay, so next one is analytical and numerical RTA. The analytical and numerical RTA, if you are working in a unconventional reservoir, multi-frac horizontal well, this is another module. These two are somehow connected because they're gonna give us independent analysis of the reserve. So we can use them as a complementary, either they are consistent and in line in terms of the reserve estimate or not. But today we want to cover analytical numerical RTA. But most fundamentally, we're going to try using numerical simulation for our tool to generate some synthetic data, and then we're going to import it to fluid material balance. I'm going to show you how. And these two are very great complementary modules that we have, but mainly we're going to focus on the multi-phase fluid material balance. So I prepared this workload. This most of the terms that you see here, the keywords are related to fluid material balance. At the end of the day, we are interested in understanding original gas inlets or what's the average reservoir pressure. And but along with these two main cases, or OGIP or OIP, we also need PVT. We also need, if you have some build-up data, we're going to utilize them. We can also use the characteristics that we see on the FMB plot for our surveillance. For instance, if there's any pressure support or not, or something like that, we can definitely utilize those directions or those lines that we get on the FMB as a surveillance method. In flow performance, we need nodal analysis, but one thing that goes into nodal analysis is this average reservoir pressure. So before starting to the main FMB, what's under the hood of FMB modules, we need to get to some fundamentals. If we get the fundamental right, then we will be able to analyze the data and hear to the data and see what the data is telling us. So let's start with the flow regime, because a critical component of fluid material balance is that we need to be aware that it works well if the reservoir is behaving as a tank, i.e. boundary-dominated flow regime is the main flow regime. So in this cartoon, you see a vertical well in the middle of a reservoir. We don't know the dimension of the reservoir. We also don't know exactly where the well is sitting with respect to the boundaries of the reservoir. So I'm gonna put this well on production, and I'm gonna see how the pressure start to propagate in this reservoir. It's very similar to just dropping a stone in the middle of a pond and seeing the ripples start to propagate. So in the first time step, or maybe first day, this is what I'm gonna see. So somebody has a question about the password. So this is the password. This is the password Whitson. It's an FMB 225 2025. So if you have access, if you don't have access to this, so it's a lowercase. W is a lowercase. Okay, sorry for the interruption. So this is okay. So it's a well in the middle of a reservoir, and the pressure start to propagate, and it's very similar to ripples that we have in the middle of a pond. So in the next day or next week, next month, this is the pressure, how the pressure is propagating. We haven't seen any of the boundary. The well hasn't sensed any of the boundary until this point, where we are very close to the edge of the boundaries. So if I have a very big reservoir, which hasn't seen, which is much larger, the boundary of that reservoir, very bigger than this reservoir, and the well is draining in the middle of that reservoir. That well and this well, basically in the sense that it hasn't seen any boundary, are very similar to each other. So it is the time that in the next time step, next month, the pressure propagates further and it's gonna touch some boundaries. So once they see some boundaries, then this we are entering into another flow regime. We call it a transitional flow regime, which we are transitioning from we are transitioning from a fully infinite acting wellbore into transitional, which have impacted by the boundaries of the reservoir. Next month, the pressure propagates furthermore. Next month, and once we get to this point, if we produce more from this wellbore, we're going to see the entire boundary. So it is exactly at this point that FMB assumptions start to be valid, and we got to get reliable estimate of OIP. So if I'm somewhere around here, my well have so far seen only half of the reservoir. We need to produce it more to be able to see the full reservoir. So and you can imagine the signals that will be sent from these boundaries to the wellbore need to travel all of these distance to be depicted, because we are collecting pressure and rates data on the surface. And so it will take a while for this signal to be transmitted to the wellbore. So for FMB to give you the correct answer in terms of OIP, or fluid in place, and we're going to show that through numerical simulation. We're going to adjust some permeability and some of the reservoir geometry to show what will be the direct impact of those on the FMB results. So this is a very quick summary. Infinite acting, when we haven't seen any of the boundaries. Transitional flow, we have seen some of them, but we haven't seen the full, we haven't explored the full reservoir boundary yet. And thirdly, it's a boundary dominated flow where we have seen explore all the boundaries. So it's very important to understand the flow regime and also appreciate how we can identify the flow regime. So there are some techniques that can help us to see if we are in the infinite acting, or it's mostly related to the, if we are working in the analytical RTA, we have some type curves that we can work through the slope of the lines and show us if the slope, or for instance, a unit slope, which is a representative flowing material balance. So let's move on, and with the flowing material balance, so it's very similar to the multi-frac horizontal wall. So as we can, if we focus on this middle tree hydraulic fracture, so early time going to be transitional, infinite acting, and the pressure propagate in this direction horizontally. And then once we see the interference from the other fracture, the pressure will explore beyond the tip of the fracture and at some point reach the boundary of the reservoir. So this is the different flow regime. Propagation is a little bit different from the radial flow regime, and it's a little bit different from they call it linear flow regime. In real life, it could be a little bit more complicated. That there could be a fault in the middle of the reservoir, which has not been identified through seismic, for instance, mapping. So once the pressure propagation reach the faults, now it needs to pass by the faults. These faults may not be identified on our seismic map. So our geologists, petrophysics, we're gonna map the entire reservoir to be my original oil in place. But what the wellbore see is basically see this fault, which is not hydraulically communicating before and after the fault, and therefore it takes much longer time for this pressure propagation to bypass the faults and reach, basically detect the entire reservoir geometry. We may go infill drilling and have another well at some distance from our parent well, and this also generates some drainage area around the salt. Similarly, with the multi-frac horizontal well, it's a little bit idealistic to think all the fractures are very similar to the same height. Could be many different geometry of the fractures. We may also do some refrac, and we may access different original reserve, which is the intent of a successful refrac. So all of these workovers, all of this intervention that we have in our reservoir can impact the result of flowing material balance. So getting back to some of the basics, the reservoir characteristics, basically the rate that we get on the surface depends on two main factors. One of them is reservoir characteristics, which is basically what goes in the Darcy law in terms of permeability, porosity, and some fluid properties, as well as the pay thickness. But the main important part of this also is the driving force. How much is the flowing bottom hole pressure, and what's the average reservoir pressure, which is the intent of FMB. So why average reservoir pressure matters for many different reasons. If you are in a conventional versus unconventional, the first and foremost is fluid in place determination. We're going to run material balance, but we need to know the size of the reservoir to run material balance rates on. We know how much we withdraw from the tank, which is basically surface production. And as a critical component that goes into the calculation is the size of the reservoir, which we determine from the fluid material balance. In this case, we're gonna show you how we can do that. More importantly is also we need average reservoir pressure for doing nodal analysis, right? The first parameter that goes in the nodal to create IPR curve is the average reservoir pressure. You're gonna do practice infill drilling. So you know your parent well, how much it has been produced throughout the time. You're gonna have an estimate of the average pressure in 800 feet away from your offset from your parent well. Therefore, you need to run a material balance calculation on the size of the reservoir to come with the estimate of the average reservoir pressure. So you can see it is justified to drill a well and close to the parent well. So pressure distribution matters, and the average pressure could be a good representation of the what would be the initial reservoir pressure for your infill well. Enhanced oil recovery, the conventional world, if we know the average reservoir pressure and we decided to go with the CO2 injection, for instance, it gives us, if we can attain miscibility, in this case, at that average reservoir pressure. So it's also important in the conventional world, reservoir management and surveillance. It's gonna give us some idea if our well is taking advantage of some pressure support from aquifer, for instance, underlying aquifer, right? And from some of those characteristics, it's gonna give us some idea about the reservoir management and surveillance, and also production forecasting, which is as a role of reservoir engineers. We basically have two main roles in their career. One of them is to estimate fluid in place, where I started with, and the other one is to do production forecasting. So for the production forecasting, also important to have the average reservoir pressure. So we highlighted the importance of average reservoir pressure, but where we can get them. So traditionally, we put the well on production and let it build up, right? And the build up gonna tell us some information about the average reservoir pressure. There's some issue with the build up, and we got this build up information. We're gonna plot them, for instance, for a gas reservoir. It's a very famous P over Z versus OG, GP from cumulative production gas. And they're going to give us some shape. We're going to draw some straight line. We're going to be in uncertainty in my OGIP calculation. And from this OGIP, I can calculate average reservoir pressure. But we know that there are some issues, especially during the shut-in times. We're going to have direct loss of revenue. So it's not recommended to have multiple, to be able to confidently come up with the OGIP. We need multiples of these lines, these points, to have a correct line that goes through my data. Right? So if you don't have these data, and if you only have end up with two data, I can draw a straight line, but it comes with a lot of uncertainty. So I have to shut the well in periodically to attain a reliable average pressure, which is directly related to the loss of revenue. This data could be sparse, and we end up with an unclear trend. That's why we studying material balance definitely have some advantages, but it comes with these disadvantages as well. But the question would be, can we determine average reservoir pressure without shutting in the well? And the answer is yes. The solution is fluid material balance, which we're going to cover here. A very simple definition of fluid material balance is we're going to show you how for a single phase oil reservoir, which everything can be determined analytically, we're going to deal with two equations. One equation is compressibility equation. It is simply compressibility is equal 1 over V dV dP. This is my dP. dV is how much I produce, and V is this initial fluid in place. And this is my compressibility definition. And simply, we use the productivity index equation, which is average reservoir pressure minus PWF, which is my driving force, QOL divided productivity. And you can see in both of them, average reservoir pressure is present. So if I simply add them up, right, I will end up to fluid material balance, which is independent of average reservoir pressure, and I can analyze my data using these two equations to come up with N, which is what I'm looking after, original oil in place. For oil, it is very simple to show. For gas, it is a little bit more complicated, but it's basically follow the same procedure here. For multi-phase flow, it's going to be the same, but the one that I will be presenting today make some assumption which make our life much, much easier. So this is the fluid material balance 101. At the end of the day, what we're going to see is some terminology here. One of them is material balance time, which you should be familiar with the material balance in general, material balance time based on math. So if you are dealing with any variable operating condition, declining pressure, declining rate, we know that all the solution is developed for constant rate production. Because we are dealing with variable operating condition, we need to have a time function, a superposition time function, which account for the change of operating condition. And that's the material balance side. And it's very simple definition for the material balance. The y-axis, this one is mass flow rate. This is called it density change, which I walk you through and just give you a definition of what does density change. Traditionally, in the fluid material balance, we deal with the pressure change, but here we deal with density change, which basically convey the same message: is change of driving force that we have, what we start with, what we end up with. And if I plot the data based on this y and x, then my data will show up on the straight line. The slope of a straight line is proportional to the inverse of original fluid in place. So that's the intent of that. So contacted pore volume is very important to understand. What do we mean by contacted pore volume? Typically, the geologists and petrophysics work together to give us to map the fluid in place, right? It's basically on the volumetric calculation. We have a K, we have a threshold for porosity, permeability, for porosity and water saturation. We're going to come up with some calculation of the contacted fluid in place. But once we drill our ball and we're going to see only a portion of that contacted fluid in place, we can see on fluid material balance. What could be the potential reason? So let's say there's could be quite big differential between contacted oil in place and what's mapped by our geologists. So to give you what could be the source cause of this difference, which we constantly get some questions, FMB technique, what's wrong with the FMB? Is the OG from FMB is much less than the OG from petrophysically mapped OIP. One of the reasons could be basically, I'm going to address that in the next slide, but gray is petrophysically mapped, blue is what has been seen by RTA or FMB, which we call it contacted pore volume. If you take a closer look at wherever we report OIP in Whitson, we call it contacted pore volume. There are two reasons for that. One, if the ball is in state in infinite acting, we know that pore volume is still growing. That's why we see how far the wellbore has seen that pore volume. That's why we call it contact. The other reason is, I'm going to address that in the next slide, which is contacted pore volume. As the names imply, it is OIP, which is hydraulically connected to well. We believe that there are a lot of heterogeneity in the reservoir. There could be shale, there could be fault, there could be shale barriers that the thickness of 1 centimeter or less, but the permeability is so low that make the hydraulic connectivity between different layers almost impossible. So those shale layers are not being identified on the seismic map or through logs, or we don't see them. The geologists don't see them, the petrophysics. Therefore, what they map is the entire pack of the reservoir, which is interbedded by all these shales, which make the reservoir kind of compartmentalized. And what the wellbore see is all the pore volume that are hydraulically connected. That's making a big difference, sometimes 2-3 times difference in what is being mapped as an OIP for via FMB or RTA techniques, or in comparison to the petrophysically mapped OIP. We believe that the reservoir behavior kind of a diffusive behavior. So if there's a fault in the middle of the reservoir, will cause the pressure to take a little bit longer time to bypass that heterogeneity and see the boundaries. So the reservoir behavior is diffusive. So it takes a little bit of time for the signals from the boundary to be transmitted to the wellbore. Also, fluid compressibility matter. If we have an undersaturated oil reservoir versus a gas reservoir, you guys are familiar with the distance of investigation, the properties that goes into the distance of investigation calculation is viscosity and compressibility. If the fluid properties are different, we are expecting to see contacted oil in place for the same reservoir with the same volumetric, with the same shape and geometry, a little bit different for if it is filled with gas with respect to if it is filled with oil. And last but not least is the PDP, pressure-dependent permeability. Pressure-dependent permeability, I have prepared a couple of examples on that, and I will present those to you. Make the data delay the signals from the boundaries. So we need to be aware of that, and we can test it, how it will impact. There are multiple ways that people can explain why PDP delay the signals. And the most easier way would be PDP as the pressure drop, the permeability also drop. So the near wellbore permeability start to reduce, and it will be more difficult for that to receive the signals from the boundaries. So that's the easiest way I can explain why PDP will delay the signals. So at the end of the day, we end up with the volume of the reservoir, but it can easily be converted to fluid in place using simple formation volume factor, solution gas and oil, and some information about the initial saturation. Do we have any questions so far? That I'm sure that have been some questions in the chat box, but if anybody wants to speak up and the question, please let us know so we can take a few minutes here to answer those questions. All good. So let's start with some theory on the multi-phase fluid material balance. The method has been developed by these two gentlemen, and we would be all very happy if you request this paper. We'll send it your way. And this is the fundamentals, how they address fluid material balance for multi-phase. And the only piece of information that's required for FMB is the PVT information, like any other method, is a rate, which is readily available on the surface on the daily basis, some bottom hole pressure. These are only three information that we need to massage this data, twist this data in such a way that we plot them. And by the way, there's no relative permeability needed. And we're going to address why not relative permeability. Despite the fact that if you're in a realm of multi-phase flow, the first question that we can ask, what's the representative relative permeability for our reservoir? And in this case, there's no relative permeability needed, which is one of the strengths of this method, that we don't need any information about the relative permeability. So once we get these three sets of data, we're going to plot them in this way. And from the slope of the line, if they present a straight line, we can convert the information to inverse of for volume, which later can be used for converting to original oil place. Other important information about FMB is the geometrically agnostic. So it doesn't matter if you have vertical wall, horizontal wall, multi-frac horizontal wall. It doesn't matter. It's only treat the data and see it's producing from a tank. So the geometry of the wellbore doesn't matter. We need to make sure that the flow regime is in boundary dominated flow. Otherwise, if we do the interpret, we can still go ahead and do the interpretation on the data, but that would be contacted fluid in place, which we know during infinite acting, it is growing. So if we have another 2 months worth of data, and we will see that the slope on these start to change, indicating that we have contacted more fluid in place. So it really helps us in combination of other RTA techniques that we have. For instance, in the multi-frac horizontal well, we use analytical RTA to come up with the estimate of time to end of linear flow. From time to end of linear flow and the slope of the line, we can back calculate the volume of the reservoir. So that's totally different technique. In combination with the fluid material balance, we can see how much fluid what would be, are they consistent, or the result from two independent methods are consistent with each other. And if not, what could be the source cause of that? Maybe the underlying assumption is not valid for one of the methods. So we're going to investigate for that as well. So at the end of the day, so based on this plot, so if our data has this slope, it will be proportional to 1 over OIP. If I'm dealing with the steeper slope, I'm going to have a smaller OIP, bigger slope, and shallower slope. In a sense, it's very similar to analytical RTA. The shallower the slope of the line on the data, the better the well performance. But here, well performance during boundary dominated flow is mainly function of original oil in place. So the shallower the slope, the more OIP the well has been able to contact. So let's get to some synthetic examples. So with the synthetic example, I want to quickly show you where in the software we're going to be spending most of our time today, and we're going to generate one synthetic case here. And so you guys are familiar with that one. So as we go through the slides, you'll get some chance to, if you're going to manipulate some of those information, you will see how we can do that. So I can see, let's see how many people have been able to generate a project. I There's 89 people on the call, so please go ahead, and 42 also 89. So half of you, please. The rest of you, I encourage you to go ahead and add your project and start working on that. So I have added my project. I can easily go here and search for my name. So it's a searchable field. I can go here, and I'm the owner of this project. So if you go to your own project, you will be able to see this empty space. So on the left, we start from the field, project, and well. Now we are in the well, so we can have as many wells that you might have in the project. And in the scenario, it's different scenario for that well. So we're going to spend some time in the PBT to generate a representative fluid properties, and then multiphase fluid material balance is here. We're going to also spend some time in the numerical model. And also there's another module here, which we will get to, is simple material balance. So basically 4 locations in here. If in the wells, if you please go ahead and add well. In the add well, I'm going to say, call it example on rain. The reason why I call it on drain, I'm going to show you something once I created my case. If you save your name, well name as this one, you're welcome to pick any name, for example one or whatever you wish to. And but the reason why I call it on drain, you will see in a few minutes here. So once you click on save, you will be directed to the PBT and click on edit reservoir fluid composition. There's an edit button. Click on edit, and you will see this window here. We have a separate course dedicated to PBT, so I'm not gonna go through individual part of these, but the method of initialization is called GOR, and my initial GOR is 1000, initial reservoir pressure and temperature. Simply click on save, and if you do so, you will end up this phase envelope. So this is my phase envelope, bubble point, dew point, initial reservoir pressure. And if you go to the PBT table, these are all the information for oil and gas. So BO, RS, viscosity for oil and gas, and some information about my initial fluid. It's undersaturated. This is the bubble point. This is classified as black oil, and degree of undersaturation is this. So this is my PBT. Now, please go to the numerical model. In the numerical model, the intent of this is to generate some synthetic data so we can use that for our analysis. And the beauty of that is that we can easily generate any synthetic data that we wish. So I prepared 5 examples here, and you will be familiar with that by the end of the course. On the edit part, you will see all the information here. This is my lateral length of the wellbore, number of fractures, permeability, etc., etc. Simply click on save, and there's some information about the grid refinement. Keep it as low. Well control. I'm gonna make a bottom hole synthetic case, and these are the information for my synthetic case. How the pressure is dropping, declining. Number of simulation days is 1000 days, and after 450 days, I reach to minimum bottom hole pressure. Before running the simulation, please go ahead on the 2D map, click on that, and select turn on 2D map, and turn on and relaunch. So if you do that, the simulation start running, and see in a fraction of a second, I will provide you the information for oil rate, gas rate, water rate, average reservoir pressure, bottom hole pressure. A very easy step to import this information as a well production history will be to go to the export button here and click on set historical data equal to simulated data. If I'm going a little bit at a higher pace, please let me know so I can adjust my pace so you guys can follow up. So if you do so and click yes, then take a few seconds to the data show up on the line, right? So this is my historical data, and this is simulated data. So my simulated data, now it is imported as a part of my production history. So this is my production history that show up here. For some information about the original oil in place, please keep this in mind. 7.2 million OIP based on this wellbore geometry and information that I put here. Now, please go ahead to the fluid material balance. And in the fluid material balance, simply click on run. Let's see what information we get from here. Is contacted pore volume converted to contacted OG, OIP, and original oil water in place. There's some initial condition, which is basically what I inputted as a PBT in the PBT section, 8,000, initial water saturation, 30%. And we're going to talk about this later in the course as well. So if you click on run, you're going to see this tree. If you're familiar with Whitson, great. If not, I'm going to walk you through how to interact with some of these plots. So in each of these plots, any plot that you see in Whitson, you can go to the corner and see double-headed arrow. You can shrink and expand. Right? You can go to the corner and see this diagonal double-headed arrow, expand it, extend it. Right? And you can deactivate some of these plots. There are some functionality here. For instance, lasso highlight. If I click on that one, there are different options. You can click on those and select your points. You can lock your zoom on the axis. So if you lock it, there's no way I can adjust this line. And you can also fit some option. There are two options, a spray gun. This is my favorite. So I click that. I can use my middle mouse button to retract and expand this the circle, so I can adjust, I can select my points on my line. Any information that we have here, it will be tabulated in table format. So you can easily copy them. If you're gonna do some more extra work on your data, you can copy them in Excel and start to manipulate those data. Reset the zoom, simply if I adjusted any of those, we can reset the zoom, and you can double click or reset the zoom, has the same functionality. So reset the zoom and expand. So it's basically expanded to get the full size of the monitor. On the right, I'm going to get to them as well, but not now. So what we're going to do right now is, you see this slide. In this slide, I presented to you the data show up on the straight line. If we have our line through the data, we should be able to calculate our volume in place. Okay? So if you click on the fit option and a spray gun, and simply click on this portion of the data. If you do so, your line will be fitted to this data. And you may need to run one more time because we changed some parameters apparently in the interface, and then we're gonna run it again. And this is the information for original oil in place, 3.4. What was the information that I put in the numerical simulation? 7.2. I almost getting half of my reserve that I simulated. So anybody want to take a guess what could be the potential reason for that? Why my FMB? Is there something wrong with my FMB? I've done something which doesn't comply with the fundamental assumptions of the calorimetry about. Anybody want to take a wild guess?
Pseudo steady state.
Pseudo steady state. Yeah, it's getting close. And we're going to check that one as well. So there's two ways that we can feel if the valve is in pseudo steady state or not. If you remember, in one of the slides I presented, I talked about the flow regime, right? This is how the valve is behaving, going to be infiniting for a while, then meeting some of these boundaries, and FMB going to give you a correct answer once you reach the full boundary, right? So let's go here, and in the 2D map, you select it to be on. If you click on that one, it shows you how the pressure is propagating in my reservoir. If I advance through the time, by the end of history, which is almost 100 days of history, we selected to be the total simulation days to be 1,000 days. So it's at the end of the history. You see, there are some regions in the reservoir that the pressure, initial pressure was 8,000, right? But the initial pressure, this grid block after 1,000 days of production, the initial pressure is 70, 79, 76. So it has not been effectively depleted. So FMB doesn't see this region, basically. It only sees the middle part region. In order to comply with the FMB fundamental assumption, let's do one more change here. And what I'm gonna do right now is to go ahead in the numerical simulation. And in the numerical simulation, you see there is an option here which set XE equal to XF. So my XE is 400, my XF is 400, XE is 800. If we click on that one, you see now any contribution from beyond tip of the product to this area, which has not been producing in 1,000 days, will be eliminated. Click on save. So the software is telling me something has changed. Now I need to rerun that. If I rerun that, now I get a new set of data. So 400, 400, save it, and export it to set historical data equal to production history. So now my OIP is reduced to 3.6 because I simply remove this external area beyond tip of fracture. I opted in my production history by exporting my data to simulated data. And now I'm gonna go to FMB. And something has changed. I have to run that again. And this is line, and going through the data. How much OIP I'm contacting right now? What did I input in the numerical model? 3.6. Pretty close, right? This is basically how we can test some of the ideas that we might have You might say, okay, what about the permeability? The permeability is 50 nanometers in my case. How would the pressure propagate in the 50 nanometers, the permeability? You can simply drop it to 50 nanometers and repeat this exercise multiple times. So it's highly recommended in Whitson. What we are recommending people, if you have some idea, you're going to test it, go to the numerical simulation, export it as a history, and then do the analysis based on the production history, which you know the answer for. What I recommended beyond that, you don't generate this data. Ask your colleague or friend of yours to ask to generate this data, not to get biased by the solution that you already know. So ask them to generate this data without giving you the input parameter, and you go ahead and do the analysis. And once you do the analysis, then provide the answer and then compare and contrast your results with what had been inputted. Okay. So if I run so fast, I'm going to repeat that exercise one more time during the course, so don't worry about that. You will be mastering that. So this is what we are recommending. Start with the numerical simulation. Generate your synthetic solution with a known answer, import it as a production history, and do the analysis based on those. Hope everything is clear to you. If you have any question, please. We're going to proceed for a couple of more minutes before we take 10 minutes break, and hopefully you guys so far enjoy the capability and the material we presented.
Hamid, there's a question in the chat box.
Yes, please.
How do you know which linear part of FMB you should choose?
Very great question. We're going to add it as what portion of the data would be represent flow and material balance. Represent, basically, we should do the analysis is under the title of the slope selection, picking the slope. The short answer would be pick the shallowest slope, but we're going to show you through real case examples, also synthetic examples, what slope do we need to pick. All good. So we started with the synthetic example. Now you are a little bit familiar with the interface, what you're going to see in the FMB, etc., etc. And can you talk about these curves? For sure, we're going to talk about the FMB, this plots okay. Sometimes if the run function doesn't work, your best friend to control all to refresh the page, but sometimes it's also recommended to control shift R, which basically you have the latest version of the software. So control all and control shift R is basically your friends. So we're gonna talk about these plots on the right hand side of the FMB. What would be how we can use this information here. For instance, we're going to talk about this one. This is the average reservoir pressure. This is the flow and bottom hole pressure. Everybody knows that the average reservoir pressure is always above the bottom hole pressure. So it could be as indication of if you pick your slope correctly or not. We will add this in the next half an hour. Also, there was very great information on the water saturation changes. Another question, does it export daily rate? We can test it. We can go to the production data. And in this edit button, you see that the initial part of these is daily rates, and then it switched to maybe 10, I guess 10 days. Yeah, seems to be daily rate, but this daily rate, yeah, seems to be daily rate export to the production rate. So I'm going to proceed with the theory behind it. So a little bit to get familiar. So we don't want to spend much time here, but you're welcome to go to the flowing material, the main paper by the authors, and so definitely help you to see, okay, what's the main assumption behind that? So what you see, this is the equation. Let me introduce these a little bit. This is mixture density change. I'm going to talk about that. You're definitely familiar with the pressure change, which is the driving force for production, right? We talked about that, the average reservoir pressure minus PWF. But in these equations, FMB, developed by these authors, instead of pressure dealing with the pressure, they dealt with the density, which is basically the same concept, right? The other piece is a mass rate. So instead of dealing with rates, with the volumetric rate, we deal with the mass rate. And material balance time, you're familiar with the material balance in the analytical RTA. It's taking care of any variation in the pressure and in the bottom hole rates, in the surface rate, basically. So all the solution developed for constant rate, for variable operating condition, we use material balance. I'm going to give you the definition of that as well. This is the slope of the line. You see the slope of this line is proportional to the inverse of pore volume. And this is simply intercept. I'm going to talk about intercept as well. So if we plot the data, this is y-axis, x-axis, and it's going to be my intercept. and this is the inverse of that. This is the graphical representation of this equation here. And let's talk about a little bit about mixture density. So you see the density at the surface condition for oil and gas and water is showing up here. It's nothing like a difference from the pressure, but things are present in terms of the density. So what are these terms here? This is simply oil saturation divided by formation volume factor. We know that in the reservoir condition, oil will be split both in oil phase and in the gas phase. In terms of in the oil phase, it is oil phase. In the gas phase, it is solution oil in gas. That's why we have RV terms here. Similarly, for the gas is we know our S term. So a gas could be present either in the free gas phase, which is simply S of gas divided by Bg, or in solution in oil, which is this RS term take care of gas in solution, and simply for water. So these are the density terms. It's very similar to the pressure difference. We talked about the density differences, and mass rate is simply what we are producing on the surface. Again, it is simply in terms of the density, simply multiplication of density and rate, which also gives us the total mass rate. And material balance mass rate, very similar to the cumulative volumetric divided by instantaneous rate give me material balance based on volume, based on rates. But here, material balance sign based on math is cumulative mass divided by instantaneous mass. So one more time, this equation, if I treat it as y, if I treat this one as ax, let's try to treat it as intercept. It's going to be very simple straight line, right? My governing equation. That's the beauty, another beauty of this simple material balance terms. So and again, if you're going to think much simpler than that, it's basically density in reservoir condition equals to mass divided by volume, which we're looking after this one. So in practice, let's see. So I generated one synthetic case. I can add some noise to that as well and present it very similar to the field case, but let's see what my actual data is presented to me. With my actual data, it's a very famous quote that in theory, there is no difference between theory and practice. So what I presented you seems very simple, but when it comes to selection of the peaks, right, the selection of the slope, which portion of the data represent the boundary dominated flow and which slope should I check? So, but in practice, there would be a lot of differences between theory and practice. So let's go to that. So we're going to talk about the 3 key period. And it's a very actual case. If you imagine an undersaturated oil reservoir, which I generated an example for, we started with the undersaturated, which initial reservoir pressure is higher than the bubble point pressure. So the pressure decline and at some point hit the saturation pressure, right, which is the saturation pressure. What's going to happen at this point? Some gas evolve out of the solution. So once gas evolving out of the solution, basically, there's going to be drastic change of the compressibility in the oil phase as well. To show you that concept, I'm going to quickly go to the PVT section. You're welcome to follow me if you wish, but you can only see what I'm doing right now here. So in this PVT table, in the oil formation on the top left plot, if you click on the show oil compressibility, let me expand this one as well. You see this is at the bubble point, right? At the below bubble point, B will drop, above bubble point, B will drop, and the bubble point, B is the maximum value. Right at the bubble point, if I'm here, this is the compressibility of the oil, which I'm reading the corresponding number on the right axis here, oil compressibility is the logarithmic. Right at the bubble point, there's a drastic change in the compressibility of the oil, which is attributed to gas evolving out of the solution. So on the saturated oil, the compressibility is of the order of 5e minus 4. But once gas evolves out of the solution, now the compressibility is one order higher. This drastic change of the compressibility presents itself in a new transient in my data. This transient, I have to let it, and you remember from the slide, I showed that reservoir behavior is a diffusive behavior. What does it mean? Any interruption at the operating condition, or in this case, PVT property of the phase, will take some time to dissipate into the reservoir because of the diffusive behavior of the reservoir. The lower the permeability of the reservoir, it will take longer time for those interruption or those transient effects to be dissipated into the reservoir. So you see from this slide, right, once we hit below the saturation point, there's going to be totally different trend on my fluid material balance, the fluid material balance trend line. So where do I pick my line? This is definitely a much better data set to pick my line from rather than this data set. So the first thing I'm going to check, I'm going to check my saturation pressure, go to my data and highlight that portion of the data and see in the example that will be created here, we can show that through going to fluid material balance. And I'm going to highlight this. There's a one feature, very nice feature here that I can lasso highlight some portion of the data. Let's see what's going on here. If I highlight this board, they also show on the bottom hole pressure. And you see somewhere here, you see the drastic change of the slope. And if I go in the PVT section, you see that the bubble point pressure is 3200. So right at the 3200 point that I see the drastic change of the slope on my FMB. So if I zoom in more and remove all highlights, I'm going to be more specific about this point. I'm going to highlight a couple of data points here and go to FMB. Shouldn't have done that. That's a highlight, save that one and see what is the following 3127, right? It's very consistent to the saturation pressure. So whenever I hit the saturation pressure, there's going to be drastic change in the slope. And this slope, I know it's coming from my PVT behavior. So I have to disregard the slope that's going through the data. Depending on how undersaturated your fluid is, to start with. So you may see this behavior early or later throughout the production history. So, but if you see this, definitely you need to pick this slope to be a representative slope for your model. And we understand here that once we drop below saturation point, we're going to see totally different slope, and it will take a while for that slope follow the same slope that we had here. So this slope and this slope on the data are very, very, very parallel to each other. So be aware of that. And then the other point would be, okay, this is the slide, a slope selection. Which slope do I want to select? Definitely I want to select the shallower slope. So once we pick the slope, then we can calculate the volume of the reservoir. And once we calculate the volume of the reservoir, we can calculate the bottom hole pressure profile, right? So one of the plots in the here was this average reservoir pressure. So this slope corresponds to this average reservoir pressure profile correspond to the slope profile that I've selected for this one. Let's do one more thing here. So I'm gonna grab my data, and this is my data. So this is basically the three regions that we presented: early slope, later slope, which correspond to this gas breaking out of the solution, and final slope, which is very parallel to the early slope. We say the slope is inversely proportional to the volume of the reservoir. So if I make a slope steeper, my volume of the reservoir is 7.1 VP, and now it is dropped to 1.7. So 1.7, if I make the slope steeper, will change to 24,000, right? And let's see if I select my slope like this, I'll run the calculation and see this is my flowing bottom hole pressure versus average reservoir pressure. And I know by no means the average reservoir pressure can drop below below bottom hole pressure. And so if I make the slope a little bit steeper, run the calculation one more time, and now this is a criteria check for me basically to make the average reservoir pressure higher than the bottom hole pressure. This is basically, this is illustrated here very nicely. If I select this slope, this is going to be my average reservoir pressure. If I check a steeper slope, going to be my average reservoir pressure, which is not acceptable here because it's below the saturation of the bottom hole pressure. And late time slope is simply I do the calculation based on this one, which is more reliable for sure, because I have started to explore all the boundaries. This is going to be my corresponding average reservoir pressure. So always pick the largest slope, and we can have a 10-minute break here before I proceed with the build-up component of that, and then we will cover the recovery factor. So let's 10-minute break. If you have any question you would like to discuss, please speak up. Otherwise, enjoy your 10-minute break, and we'll see you in 10:16 CT time. So with the slope selection, we have a couple of more dedicated slides for the slope selection based on depending on what information we have from our data, right? For instance, if you have some build-up data, that would be very critical, useful information to combine with our analysis to help us determine the slope. Sometimes the data, the noisiness of the data wouldn't allow us to basically select the data that represent the boundary dominated flow simply because the data are noisy inherently and we can't do anything about that. There are some tools that we can utilize, like integral, which basically dampen those noises. But in general, if you have some build-up data, that will be really useful information to use. So we will address that shortly in the next couple of slides. All good. Thank you, folks. Let's get started again. So I see a couple of questions. I try to just address them here as much as we can. So with the pressure heat map, you were interested to see the pressure heat map. So if you go to the numerical model, in the numerical model, and there is a 2D map, and once you click on that one, maybe it doesn't show up. If it doesn't show up, you need to refresh. And so in the numerical model, the 2D map, first of all, if you want to run it, you need to make it on first. So if it is on, then you will be able to see how the pressure is changing. There are a lot of functionality here. There's a pressure, oil saturation, gas saturation, water saturation. If you have different layers, you can also select different layers, and you can also have the bird eye view versus side view. So all of them are available here for your reference. And the other question is export the data. Let's export the data. Simply go to the export on the top right. And there are multiple options here. Daily rate, monthly rate. So if you export, it's going to be in Excel. There's one option here, set historical data equal to the simulated data. So this is what we simulate. We're going to set this one as a history of the data, right? And the other question is linear part of FMB. So I already addressed one of the issues with the multiphase FMB when we are dropping below saturation pressure. We totally see a distinct slope, which is much shallower than what it used to be before hitting the bubble point pressure. The reason for that, what I believe is happening, gas evolving out of the solution. Gas is much, much more compressible than oil. We saw that also from the PVT behavior, and that compressibility of the gas, which make the investigated area very close to the fracture phase. So that caused the interpreted volume of the reservoir to be restricted around the fractures. We need to give it some time for that interruption, not interruption basically, but a transient effect that happened in the PVT this time, not in the operating condition, in the PVT to be dissipated in the reservoir. So that's the selection of the slope in the multi-phase flow. Where can I get the example one on drain? So I make my project to be, so in a project, if you search for my name, there's no company-wide, so you should be able to access this one and see what information I included in the case. How will the plot look like for the rich gas condensate? So I show you the recipe and prescription how to generate a case for the rich gas condensate, but you can easily go there and I can show you. So in this example, in a rich gas condensate, the only thing I did was as an idea in the PVT section, I adjusted the initial total gas GOR to be 5,000. So this is shown to be the phase envelope. And this is the temperature of the reservoir is higher than the temperature, critical temperature of the fluid. If you go to PVT section, you see this is almost 200 CGR, which is classified as a rich gas condensate. So take a look at this case maybe. And also I provided you as a representative sample for a gas condensate. So you're welcome to try this one as well in the edit compositions. There's a method that's a fluid composition, right? In the fluid composition, you have this information for the gas condensate near critical wet gas. So you may try this and see what phase envelope you will get, right? So that's a simple way to generate gas composition for the gas condensate reservoir, and then you can go through the same step that we try here. How does pressure diffusivity behave in a low pressure gas reservoir such as Hengstman? Great question. Pressure diffusivity will be identical in any reservoir, any fluid system. But with a low pressure reservoir, yes, only the PVT that matters at this point, which is going to be the PVT of gas at high pressure, which behave very similar to liquid. Gas at high pressure, 10,000 psi, in terms of the compressibility, become very close to the liquid. But there is other factors that may be also in place for Haynesville. It is famous for pressure-dependent permeability, which I have one dedicated example for pressure-dependent permeability that may impact that. So pressure-dependent permeability is permeability of the reservoir as a function of pressure. As we deplete from the reservoir, the permeability of the reservoir, which is related to the pore throat, will be changed because those grain size under high stress, as we deplete, will have a smaller pore volume, and therefore the permeability drops. So we're going to have one dedicated example for that as well. The other question is for reservoir P reservoir less than P saturation. We are initially in the two-phase slope of two-phase. Theoretically, the method should work. And the simple way to test it is to generate the synthetic data using initially for a reservoir in a two-phase condition and generate the history and import those history as a synthetic production of the well and analyze their data. So these are some of the questions. And let's pick up where we left off. And this is a selection of the slope. Definitely the shallower slope correspond to higher OIP, the bigger slope correspond to correspond to the steeper slope correspond to a smaller OIP. So this is the first check that we need to do is to compare bottom hole pressure against average reservoir pressure gap. Pick the shallowest slope. This is the correspond to the largest pore volume. The other piece of information that we might have, which could be very, very useful, is the build-up data, right? So this well is taking advantage of this information here. We can visually project the trajectory of the build-up and say what would be the average reservoir pressure if the build-up continue for a month or 2 months. So we're going to take advantage of this data and we're going to adjust our line on our data. In this case, let's say the data is very clean data. So let's try putting some lines on this data and see if this is my line, it's going to be my average reservoir pressure. Definitely violated the fact that average reservoir pressure should be higher than the bottom hole pressure. If I adjust my slope a little bit along this line, then I'm going to be this average reservoir pressure. I have to pick a slope sometimes that still it doesn't go through the line simply because of the multiphase effect or some other things that are going in the reservoir, which is not included in FMB. But we're going to adjust our slope if we believe our build-up data. Right? If we believe our build-up data, we're gonna adjust our slope so the average reservoir pressure is higher than the build-up profile that we have. So if build-up data are present, and there could be a lot of reasons why the build-up data are not trustworthy because of the dynamic of the wellbore. But if those build-up data are available and we do some due diligence investigation that they are trustworthy, we're gonna take advantage of them a lot in the FNP, by the way I presented to you. So there could be some other reason, like an external event, like fracking. So in the case of fracking, I know this is PWF. This is the calculated bottom hole pressure. In this case, this bottom hole pressure is definitely not a build-up. It's not similar to build-up at all. So my build-up wouldn't behave like this. I'm gonna be more asymptote to bed over and plateau. But in this case, this is a fracking. So I can simply disregard this information here and set my average reservoir pressure to go through this data. So that's something that to keep in mind. For undrained case that I presented, I run it only for 1,000 production history time, right? So if I run it for instead of 1,000, 2,000, then I will be able to drain the region beyond tip of the fracture. So what we're going to see here, so if you have limited data, I'm going to run my slope based on this one. So my OIP is going to be translated to 500. If I have this much data, then this is a slope. I have this much data. This is going to be my slope, and my OIP is going to be 3.5 million. And my OIP is going to be stay the same because I explore all the boundaries in the reservoir. So in this case, this is the true slope. We know the reservoir very well once we abandon the reservoir. So this is a very famous quote, but we try to take any data that we can have, we have, and interpret those data to come close to the true actual OIP. So this is identify infinite acting. This is boundary dominated. A couple of conclusions here. Picture shallows and slow. Trust if the data on the buildup are trustworthy. Take advantage of them, adjust the slope so that you meet these two criteria. Fracking and some other external events should be identified and be disregarded and treated properly. And with the infinite acting, we exploring OIP during boundary dominated flow, we are capturing the full reservoir size. Do we have any question that you want to ask? We're going to proceed. So these are the examples that we addressed. These are the questions that we addressed. And so there's one question, if there is any advantage of using density-based analytical equation as opposed to pseudo pressure approach. Well, density and pressure are kind of the same. In people start with the pressure, and a gas use pseudo pressure. So for a gas single phase flow, uh, we tend to work with the pressure and pseudo pressure. And for this FMB, the authors presented in the density format, simply because the equations show up as a density. So we start with initial mass in the reservoir. As a matter of fact, we write the mass material balance. We don't do volumetric material balance. We convert mass to volume by density. So the original form of the equation is in the form of density. Right? Simply because we are reporting rate, we don't report how many kilograms per day this well has been produced. We report rates. We are comfortable with rates. Has been traditionally done so, right? And but originally everything is started with a mass. We convert mass into volume through density. So we are welcome to use mass, density, volume. If volume goes with pressure, and mass goes with density. So this is how the equation shake out. So let's talk about the complementary part of this FMB, which is recovery factor analysis. And if you're going to get some idea about which part of the software we are talking about recovery factor analysis, this is basically in the recovery factor. This is this part of the reservoir, right? So this part of the software that we're going to talk about the recovery factor. Okay, so one thing, I'm gonna repeat one more exercise here that show you it doesn't depend because I changed the PVT, so it's looking for the PVT information here. It's not running. Before I cover the recovery factor, you're welcome to follow me, but you can also only see what I'm trying to do here. As part of the slides I showed you, that is basically geometry agnostic, well geometry agnostic. It doesn't matter if I'm draining from a tank via a single vertical wellbore or multiple horizontal wellbore or multi-frac horizontal wellbore. To show you that, I'm going to add a well here. I'm going to call it example 1B and call it hyper. You have access to my domain, so you can easily see what parameter goes if you want to follow up later. Goes into this model. So for the PVT, I'm gonna stick with the default here, and right, I'm gonna go to the numerical model. In the numerical model, so I'm gonna make my numerical model, which is originally for the well reservoir data for multi-frac horizontal well, but I'm gonna make some adjustment here. First adjustment I'm gonna make is I make the fracture half length to be 1. I'm gonna make it 1, and then I can also adjust the length of the wellbore to be 3000, the except which is half length of the reservoir to be 1500. And I'm going to make it look like it's a conventional reservoir. So by conventional reservoir, let's start with the 2 Darcy, 2 milli reservoir. So it is 2 macro Darcy, 3 more 0, make it 2 milli right? So this is 2 milli reservoir right now. So if I click save, copy these numbers into your model, it's 2000, 3000, 1500, and 2000. So the only 3 parameters I changed on this model. And run it. So this is my simulated data. I want to export it as reservoir history, well history, yes. So this is my data, as easily as that. I created my model. Now, if I go to FMB, so this is 7.7, FMB, click run. This is exactly when I hit the saturation pressure. We can confirm that later, but I already showed that to you to see I'm getting close to 7.4. So it doesn't matter if I'm in a milli-Darcy domain, you're gonna hit the boundaries much quicker than if I'm in a macro-Darcy. But if I'm in a macro-Darcy, it takes much longer time to hit the boundaries, right? So this is one of the examples. And let's go on the recovery factor concept here. So recovery factor, it's basically connecting original oil in place with respect to EUR. So we already calculated the volume in place. This is correspond to contacted fluid in place, and then with the contacted fluid in place. Now, if I have this information, then if I have recovery factor, I can calculate original oil in place to EUR, right? This is the intent of recovery factor. The beauty of this is physically constrained. This is based on some physics, which is the honoring material balance. Therefore, it is physically constrained. And then I can easily convert the recovery factor from the fluid material balance module plus the OIP that I calculated initially to convert to EUR. Yeah, so that's the intent of that. So where this equation is coming from is simply from this equation. You may say, oh, it's very complicated, but I can quickly walk you through what's going on here. So NP divided by N is simply recovery factor for oil, GP divided by G recovery factor for gas. There are some terminology here. All of these methods work on the cumulative water-oil ratio and cumulative gas oil ratio. So cumulative gas oil ratio is GP divided by NP. Oil ratio is WP, cumulative water divided by cumulative oil. There are some terms here. So I'm going to say it's very easy to follow these terms. If you simplify it a little bit here, there's the N term here, which is if the reservoir is initially undersaturated. So there's a gas gap, right? Sorry, if the reservoir is initially saturated, if there is a gas gap or there's a multiphase flow, it will start with. So these terms here is the expansion of rock and water, right? Because there's a delta P here, there's a compressibility, simply the expansion of gas and this expansion of water and rock. This term here is initial RSI minus RS at today at averages of operation. So it's how much gas evolved out of the solution multiplied by BG, simply gas at reservoir condition. So despite the fact that this is like a little bit complicated and convoluted, but it's really easy to follow if you know where to start to develop this material balance equation. And a recovery factor at the end of the day depends on the PVT, on the abandonment, cumulative production, cumulative OGR, and cumulative water gas ratio. I'm going to show you how we can calculate the recovery factor as a component of that. So this is the steps that we need to take to calculate recovery factor. For it to happen, we have some production history that we have to forecast how the OGR look like in the future. And that's basically the necessary step for the recovery factor analysis. So we have some idea what would be the trend of CGR look like in the future, and both for the CGR and water gas ratio. So we're going to show you in a few minutes how it look like. So if your well is producing above saturation pressure, right, the CGR or OGR oil gas ratio going to be flat. So I will create one example to show you. In this case, you will end up to predicting the entire trajectory of the oil gas ratio below saturation point, which heavily will significantly impact your recovery factor for the oil. So we will try a couple of examples to adjust these lines and see how the recovery factor is tied to this profile below the saturation pressure. So why do we need relative permeability? If you remember, I started off with that question, and the question was why no relative permeability is needed. In fact, relative permeability is somehow embedded into our data. So relative permeability plus PVT is the fluid ratio, right? And let's see, we are dealing with the water-oil ratio, oil gas ratio, CGO, water-oil ratio. These are all the ratio that we are dealing in our fluid material balance analysis. Let's see, for instance, in the case of gas-oil ratio, we know that some of this gas-oil ratio coming from gas in solution in oil. The rest of that is simply the ratio of the mobility of oil and gas, right? And you see, we have this information. We have some PVT information. These are the PVT information of the oil and gas, and relative permeability is inherently embedded into this producing gas-oil ratio, and therefore we somehow accounting for relative permeability in the data, right? We don't input them, but if we adjust relative permeability in my numerical model, those will be represented by adjustment of the profile of oil and gas in the numerical simulation. So when I import new data based on new relative permeability, those are already captured. So recovery factor in Whitson. So I'm gonna walk you through now one case for the recovery factor, and please follow me for this example so you have a good understanding of what's going on here. So if we go to the recovery factor, let me explain the theory first, and then I walk you through these three locations in the solver. So all of this all of these methods, recovery factor, flow material balance, as well as simple material balance, numerical model, they should in fact generate the same recovery factor numbers if we keep two numbers cumulative GOR as well as abandonment pressure between three of them. So that's the purpose of, that's the goal of this exercise. And it is shown where if you go watch, if you take a look at one more time on these equations, on these equations, you see that the recovery factor, the only term that goes into the recovery factor is cumulative gas-oil ratio, and also some PVT properties, which depends on the abandonment pressure. So let's go and do one more exercise which highlight the importance of this, and in the numerical three different methods for calculating recovery factor. So if you go to well screens and if you add a new well, and I'm gonna call the name of the well to be example recovery factor, or whatever name you wish to have. New well, recovery factor, click save. So in this case, I have to refresh my page. Example recovery factor. So for the PVT, keep for the scenario, the information that goes for the well and reservoir, keep everything defaulted. In the PVT, click on edit and save. And this is my PVT, default PVT. And then on the numerical model, so this is the information in the numerical model. The only thing I want you to do, please go and set XE equal to XF, so we don't leave any undrained region beyond fracture tip. Close up save, and once you do so, go ahead and run your model. The only adjustment I want you to please do in order to make it like a time type behavior, I want to bump up the permeability instead of 200 nanodarcy, make it 1000, please. So that's the only change, plus XE equal to XF. I can run my simulation history for a longer time to basically convey the same message, but in order to make it time type behavior in 1000 days, the other alternative would be to bump up the permeability so the pressure propagate quicker and reach the boundary. So click save and run your model, and once you run it, there's a PVT composition, and then you can export your method data as a production history of the well. So this is my production history. Now on the bottom, you see this is the gas GOR. This is instantaneous gas GOR. I want you to click on the use cumulative, and once you do so, you see at 1000 days, I'm getting 2627 to 2627 SCF per STV. So we're gonna keep this number in mind, 2627, and you see I run the bottom hole pressure is 1000. So this is the only two information, 1000, 2627. If you scroll down all the way, you see there's a section here, say virtual PVT lab, and there's the one module here, say simple material balance, and here. So this is populated by whatever I set up in the PVT section for the GOR, initial reservoir pressure, etc. Surface process, keep it as is. And in the material balance input, go here. There's two terms. One of them is pressure, please put it 1000. The other one is cumulative producing GOR, 26, 27, I guess, right? 26, 27. And click save, click run. So this is my material balance calculation. It's perfectly assuming that it's a time type behavior as a PVT cell. Basically, I drop the pressure to 1000 and my cumulative GOR is this much. So what I'm gonna do, copy this one and put it in my slide deck for the sake of comparison, right? And then go to the numerical model again. In the numerical model, for the recovery factor of oil is 23, recovery factor of gas is 61. I'm gonna copy this one as well. How comparable they are, right? This is graded numerical simulation, very fancy, relative permeability, grid, etc., etc. A lot of calculation in the background. This is simple material balance calculation. It's very close to each other. It's impressive. The main assumption here is that your reservoir model should behave as a tank. If I do the same exercise during the infinite acting period, we will definitely get very different numbers. So these are two of the methods, simple material balance and numerical model. Let's go and try the recovery factor module. So we exported our data, and if we go to the fluid material balance and click on run, I have to confirm two things. First, if my fluid material balance give me the correct slope, I'm gonna go with this slope here, shallower slope. So 3.5, my FMB is 3.6. My numerical model is 3.6. Right? this one's 3.5. And if we go to the recovery factor, so for the recovery factor, there's the checklist at the bottom. Let's say we need to accomplish these steps before we calculate the recovery factor. The first one is run material balance, which we already did. And to just get you familiar with this interface here, there are 4 plots. On the bottom right plot, this is the FMB. It's a copy of the FMB that we threw our line through the data. On the top one is the OGR and water gas ratio. We have this much history. We should be able to forecast how the OGR will be projected in the future. We can do basically 2 different ways. One, we can extrapolate these lines beyond this data point, which I show you shortly. The other one, if we have some analog wells in the area, I'm going to use those information as a representative of what my well is going to produce in the next couple of years, right? So to be able to properly function with these plots, what I want you to do, there are some other functionality for zooming. If you click and drag your mouse horizontally, you'll see it will only expand. It will maintain the vertical zoom and expand the horizontal zoom. Now, once you did so, go ahead and lock the zoom. If you lock the zoom, therefore, you're going to be staying in place like this. Then there is a button on the top. It says add points, right? If you click on add points, say during the history, I can see how my OGR is changing. This is the profile of the OGR. In the future, I'm going to see, okay, this is going to be my trajectory. Why this is going to be my trajectory? Because there are 2 guidelines for us. One of them is RV. The other one is 1/RS. The most usefulness of this RV here is guide us that, especially for the gas condensate, that the tail part of this data tends to go upward. So I'm going to mimic the same behavior for my actual data as well, right? So once I do this, I accomplish another checklist item here. I should do the same for the water gas ratio as well. So I'm gonna lock my zoom. I'm gonna be some trajectory. I know my water gas ratio would never go to 0, so I'm gonna asymptote it to somewhere here. It's really important to continue these points below the pressure that you're gonna forecast your data. So there's some information. So you see it's also a check mark here, accomplished water gas ratio. Now I'm ready to go and run my model. But before that, I'm gonna make you familiar with different part of these. This is the estimate from fluid material balance. This is the exact numbers that we do the analysis in the previous section, in the fluid material balance section. There's a recovery section, which I'm going to go ahead and calculate. There's the reservoir abandonment pressure, which I should provide some information on. And here is the information on the abandonment pressure, right? In the numerical simulation, let me show you the numerical simulation one more time. If you remember, in the numerical simulation, I set the final bottom hole pressure to be 1000 psi, right? This is the minimum bottom hole pressure. So in order to make an apple-to-apple comparison, I will go ahead and make the same assumption here. So I'm gonna go, instead of 7,000, I can make it 999, which is close to 1,000, and therefore it's gonna be my trajectory. So I accomplished the checklist. This is my profile for prediction of the OGR, water gas ratio. If I click on run, I calculate this one, the recovery factor, to see how close I am to what I have already calculated from numerical model and from simple material balance calculation. So this is the result, recovery factor. We're going to copy that as well, recovery factor, and put it here. So 3 independent modules, very close result, 23, 60.23, 22. I didn't make up this story, by the way. It's just I did practice. We can do any other case study if you wish. But you see, these methods have definitely different assumption in the background. Once the reservoir start to behave like a tank, all of them it's critical to make all of these recovery factor numbers close to each other. I would be surprised if I was not able to make them consistent. So now that we are talking about the recovery factor, I'm gonna make some adjustment to this curve, and on the fly you will be able to see how much of impact what it had on the recovery factor, especially one of the slides that we presented here. You see, this is the trajectory of the recovery factor. So if I'm producing for this much of the, so now so far in my model, I have produced quite extensive range of bottom hole pressure, right? But imagine I truncated my data at this point here, then I could have different trajectory for my line. So one idea could be maybe this is my profile. So there's some functionality, by the way, for this data point. If you work with the bottom hole pressure, if you want to make customized bottom hole pressure profile, you have already been familiar with this one. So you can grab these points and simply throw it away. The data is gone. You're going to add another point, simply click on that one. And so you can adjust it on the fly. You can elevate this point for another profile. Just exaggerate it a little bit. I'm going to show you a couple of messages here. If I exaggerate this data, this profile, to see how much of impact it had on the recovery factor. So I want to ask a question. So now that I elevated this data point, would you expect recovery factor to go up or down? What's your thought on that? So we're going to see that if it's going up and down, but directionally, now that I'm predicted higher original gas in place, so higher oil gas ratio, I'm expecting a recovery factor for oil to go up, right? If I run it again, it didn't change much, right? So maybe for this case, could be a little bit insensitive to data or not. So we can try it one more time. Before I tried one more time, 2352, it used to be 2360. Okay, maybe it didn't run at all, right? Okay. So there's another plot here, which is OGR versus oil. So this plot is also very important to take a look at. So you see what I'm expecting for my data to show basically the gray data, which is my forecast, be aligned with the trajectory of my history data. So also in the numerical model, in the numerical model, if I go one more time to the numerical model, we can see how the OGR cumulative OGR, sorry, the GOR is the trajectory of the GOR that we are expecting is plateauing in this one. So we can use numerical simulation as a guideline for how to forecast the rest of the OGR. Do we have any question on the recovery factor? Take silence as no. So we're gonna continue on the slides here. Okay, these are some of the guidelines. You should be definitely aware of that. I'm sure some of you already know about this, but it's really important to, so we barely touch any PVT information. So we didn't investigate if the bottom hole pressure is correct or not. We assume they are correct. If not, we need to spend some time to make sure that the bottom hole pressure are reliable. So they are not influenced by any external event that's not the reservoir effect. So because any of the analysis is impacted by bottom hole pressure profile. We should be able to differentiate between the wellbore and reservoir effect. We are analyzing reservoir effect, so our data shouldn't be impacted by wellbore. Wellbore effect could be drastically change the data that's coming from the reservoir. It could be dynamics in the wellbore effect, could be like liquid falling in the reservoir, building liquid loading in the reservoir, which could drastically change the interpretation. We need to integrate all of the sources of the data that we have. Talk to the geologist, petrophysics productions, intervention in the wellbore, artificial lift that we have conducted. If there's any offset production from the same operator or different operator which impact our data. So we should be aware of those activities in the area before we do the interpretation. If there's any operational changes, there's an offset bill activity, be aware of that. There's been workover. I will present you some of the examples on the real field application of these FMB that people have done on the field data, and show you if there are infill drilling or if there are workover, how would it impact the analysis. At the end of the day, it's important to think about the system-wide, which is include not only the reservoir. We are taking, investigating and analyzing the data for the reservoir information and characterizing the reservoir properties, but we know that the reservoir is attached to the wellbore, which is attached to the surface net. So the true performance will be to through analysis of all of these all together. So we are definitely aware of wellbore storage effect, which can mess really the data. And so this is very similar in the same lines of being able to decouple the reservoir effect from the wellbore effect. And similarly, in the different language and terms, well operational and completion, data integrity, interference and offset activity, and performance benchmarking. This is a very important part, as I presented to you in the very earlier slides, where FMB is sitting in our toolkit. We should know that we have a recovery factor and estimate of volumetric we should be able to compare them against other tools that they have in our toolkit, right? We have PNR decline, DCA, RTA, and PTA. So we need to do cross-validation of those, right? We already showed very usefulness of having build-up data for the FMB, which is if we pass the sniff test of it's a valid data, we should honor those, and some other stuff as well. So let's talk about a couple of examples. There are 4 field examples, great examples. The great thing about this example is that a lot of them are published. So you will be able to dig deep into those papers and just present them to just make sure that you're familiar with this, the opportunity of being able to recreate some of these data yourself. And it's not limited to a single well study, but multi-well study. And we know that a single well, FMB works best if a well is isolated by itself, is draining happily from a single tank. But in real life, we know that there are going to be a lot of interruption from the offset well activities, infiltrating, etc., etc. So it's one of those examples. So the parent well has been producing by itself for a while, for 2 years, and then there has been some infill well activity and some workover. These are inevitable operational offsets. So we need to be able to equip ourselves and knowledge so we can how we can treat this data, right? So these are some more information about these wells. Somebody asked a very valid question about initially saturated volatile oil, right? This is a perfect example that validate the capability of the method to also accommodate more complex phase behavior initially two-phase flow to start with, and you can start with the synthetic cases, but this is also a great example. Downhole wages is definitely priceless. It's precious to have those information. More data that you have is indicate that well, we are happily and peacefully with the assumptions of fluid material balance, and some more information here. The big part of this is the quality of water production. In the multi-frac horizontal well, by no means we can say we can have some idea about decoupling. What's the water is coming from the reservoir, or is the flow back water? How long had it take, or has been frac into other layers? Our frac unintentionally penetrated the layers that has been saturated with water. So we are producing some water which is not the reservoir effect. So these are the important questions to be able to address. And also usually with the petrophysics and geologists on the team, we need to talk to them, right? And we need to convince them that the true OIP is what the story that the data is telling is not what we are volumetrically mapping. Volumetric mapping is just guesswork. From my own experience, when it comes to discrepancy between OIP from volumetrically map and from fluid material balance, I definitely invite my geologists and petrophysics on the team to a coffee and donuts. I know it doesn't help the data to reconcile, but it definitely helped the conversation. So that's from my experience. So let's take a look at the data. This is the initial analysis, starting with the 30% water saturation. So this is how my data look like. Let's do the analysis. So there is another part here. I'm going to quickly show that to you. Another extra information, which is delta P average, right? So delta P, the delta density difference at average reservoir pressure, where we can find it if we go to the fluid material balance. Click on, it's not really coming back. Oh, this one's the one that was not mine. So this is my model. If I click on this one, by default, it is it's not displayed. But if you click on this one, it shows you basically this purple line. This is basically calculating the average pressure, treating the reservoir as a tank. So there are some usefulness towards that. I'm going to show you what will be the usefulness of that. So it was recommended that the best practices to utilize this FMB to present this data on the same plot and see if the well data dip below the average data. Right? If it is going through below the average pressure, it doesn't pass the sniff test. So the other criteria is take a look at the average reservoir pressure. The other criteria is take a look at water saturation. So I'm going to walk you through this one. So water rate quality, I know that this is flowback data. So this is not the true reservoir effect. So I blame it on the bad quality of water production rate. But in general, I see my data is all of my well data is above the average reservoir pressure. So this is the first check mark I'm getting. The next one is average reservoir pressure, bottom hole pressure is meet this criteria and meet this criteria that the average pressure is above the build-up profile as well. There are some outliers. It's definitely not the true reservoir effect simply because the rate is not being calculated, or maybe the bottom hole pressure is suffering from it's not being calculated properly. And therefore, it is I can safely ignore these data. The third one is the water saturation profile. Somebody asked about whether the plots on the right-hand side would be useful for, and so it's the water saturation profile, and we see there's a drastic change from 30% to 5% for the water saturation. So I'm gonna show you something here on the PVT side of the thing. So you see in the PVT table, if I include the compressibility of the oil, you see on order of -5, 10 -4, 10 -5, 10 -3 order. For the gas, I can also include the compressibility of the gas, which is of the same order, similar to oil, and even higher because it is simply gas, right? So the compressibility of oil and gas is much higher than the compressibility of water. If we're gonna get an idea about the compressibility of water, if you click on this user manual, there's a question mark. If you click on that, and here, simply type water compressibility. So there's a water compressibility to show up here, and these are all the equation for the water compressibility. There are some correlations, and this is how it is calculated in Whitson. So all the information for the PVT properties of the water is listed here. Similarly, if I go to, for instance, FMB, in the FMB, if I click on user manual, it will directly guide me to the multiphase volumetric balance. So what are the usefulness of this method? So pretty much all the theory that we presented in the free so far is presented here as well. Plus a lot of webinars from the authors and a lot of applications, etc., etc. So please make sure that you get familiar with the manual as well. And definitely there are much more beyond what I presented to you today. So if you get familiar with those, that would be awesome. So this is the water saturation. We know that the water compressibility is much less than the gas compressibility. So I'm not expecting water compressibility to drop so significantly. So what we can do with water right now is there's the two alternatives that we can do. First of all, we say, okay, maybe we need to reinitialize initial water saturation, go with a different number, and maybe we simply because we know that maybe we have some other information, extra information from our geologists, and there could be some layer barriers, some layers that is bearing water, and we are factoring into those. So those are not the reservoir effect. So let's try to do both of these alternatives and see. I'm gonna adjust my initial reservoir pressure instead of 30% to 70%. And if we do the same analysis, we will see still, if you compare the initial oil and gas in place, it's very consistent with what the analysis in the first place with 30% water, including 70% water saturation in my tank. What would significantly change the scenario here is the volume of the contacted volume, because initially I started with the 30% water, a tank that's filled with 30%. I forced the model to produce cumulative water that I have as my history, and because there's a small amount of water, the saturation of the water drops significantly from 30% to 5%. If I bump up my initial saturation to 70%, this is going to be my profile, which is more realistic and consistent with the compressibility of water. But if I have 70% tank filled with water, and I still want to produce the same amount of oil and gas off of that, my tank should be much, much more bigger, right? And this is in this case, it is 21,000. In the previous case, it was simply 10,000. So I have to double the size in order to get the same volumetric thermal production on the surface, and also comply with the fact that water saturation. So which scenario would you like to believe? In this case, it's definitely going to impact my well spacing quite significantly, right? Because this reservoir is 70% saturated, so I can only produce a certain amount of oil and gas, and not much reserve to chase underground. So that's impact of well spacing practices. And the other piece here is simply say the water is coming from some other layers. We don't want to include it in our analysis. And there's an option here to not to include the water. And in this case, the early data is much neater to deal with because simply this data is doesn't include the water impact of water. So the author then presented the lines that goes through each of these portion of the data. For instance, when the infill comes on, so this black line shows the if we account for 600 days of the data where the parent is standing by itself, producing by itself, it's not being upset by the infill. So when the infills start to show up, start to produce, we clearly see the change of the slope in the early time, right? But it takes some time to reestablish the volumetric and stay on the same parallel line to the original line. And so basically the parent and infill start to fight for the reserve. So initially the parent lost the game because it definitely clearly shows less volumetric, and then it start to regain the volumetric. So this is the type of analysis. On the bottom hole pressure, we know that this is the impact from the infill, so we safely can ignore it. When those interruption is gone, then we again preserve the criteria that the average evaporation is above the saturation pressure. So this is exactly it. And one more thing here is about the compressibility of the compressibility. So there are some guidelines that can help us if we set our lines here, but the data are presenting a different line here. What does it mean? I can quickly show that to you through one example here. That so I'm going to show you one example that you can follow me, or you can you're welcome to do it later on the impact of the compressibility. I'm going to quickly show you how you can do that. So this is the compressibility, so rock compressibility. So what I did, I basically with the same PBT data, with the same PBT data, the only thing I did here, adjusted here, was the initial GOR, because I want to preserve my data above saturation pressure. So the compressibility of rock and compressibility of the fluid becoming almost in the same ballpark. And then in the numerical model, I generated this production data, and I kept my bottom hole pressure above saturation pressure. So there's no two-phase flow happening here. As you see from the GOR, it's pretty flat. And then in the FMB, the number for the compressibility that I use here for the compressibility of rock is 4E minus 6. Now in the fluid material balance, this is my data, and this is going to be my line. So initial compressibility is 4E minus 6 as per on this model. And so this is my true volume in place. And you see the line and the data are presenting very similar parallel lines. Now, for the sake of exaggeration, I'm going to artificially bump up the rock compressibility to 40 and run this again. And you see the line shows the data are showing presenting this slope, the average are presenting a different slope, right? So they are not consistent. It is basically the message here that if they are parallel or not, and this is the conclusion from that. You can test it yourself, and vice versa. I'm gonna drastically change the compressibility of the rock. The original compressibility is 4. Now 1/10 of that is 0.4. And running one more time, I'm gonna show you how the slope is changing. So this is definitely showing a different slope and crossing each other. So this is the compressibility, how the impact of the compressibility would be. And let's move ahead. And so these are about the summary of the case. The second example is the refract in Eagleford. Let's start with the synthetic example. So this is my original bellbore completion. Then I developed it more fractured. I developed this by putting more fracture. And refract, a successful refract, is simply adding more reserves to the portfolio of the well. And it's not simply accelerating the reserve, right? This is the simulated case. So we simulated one example where we did the refract, so the rate bump up quite significantly after some period of time. And then we're going to analyze this data on the FMB to see how they look like. So this is when we do the analysis based on the clear refract data, and then when we do the analysis based off the refract data. So we clearly see that FMB is able to account for additional reserve due to refract before period and after refract. So it's all double. It's a synthetic example, but in this paper, this very nicely great example and data set for how the actual refract data would look like. And so let me walk you through. This is the sample set. If you're interested in this paper, which I highly recommend and encourage you guys to take a look at, there are much more information that we are delivering here. And so they basically presented all of these, what the slope to pick, early time, late time data, and there could be three scenarios based on the refract, right? The early time data may be much less than the late time data, which in this case is identified that the wellbore is still exploring for the boundaries of the reservoir. It's infinite acting, and then it's going to be boundary dominated flow. And late time data is equal to early time data. It means that mostly in a conventional world, it's very, or in a multi-frac horizontal well with elevated permeability or maybe tightly spaced fracture, we're gonna hit go from infinite acting to boundary dominated flow in a fairly in a fairly quick amount of time. And lastly, it could be early time data bigger than late time data. So one of the theory behind this is maybe there are some natural fracture in the reservoir. So at a high pressure, initially when you produce the reservoir, these natural fracture are open. When you deplete the reservoir, these natural fractures start to close on themselves. So we're going to lose some productivity. We're going to some linear flow parameter of the wellbore. We're going to lose some reserve. So in this case, the early time data show elevated volume in place, but as the time goes by, clearly the data shows itself to be the slope becomes steeper and steeper, which happens to be in this case, right? The early time data is 2000. After producing, it turns to be 6000. So we lost some of the volume in place. This wells has been producing by itself, so it's not an external effect. It's basically is not able to produce from those productive regions at high that used to be at high pressure when the natural fracture was open. But more information is provided in these papers, so please take a look at that paper. And here is an example of a successful refract, how infill well affected. Okay, yeah, we're going to talk about infill well. How to get the paper? We make sure you will get the paper along with the follow-up email that we're going to send out later today or tomorrow. So you will get the paper, you will get all of those information. So the beautiful thing about the FMB, so for at least for this subset of faults that we are investigating here, is only within 15 days after refract, it shows a clearly distinct slope with respect to the early time data. So it clearly shows that refract has been successful. How do we define a successful refract? If we are able to add a reserve to our wellbore, we're going to call it successful refract. If it's simply accelerated reserve, it doesn't call it successful refract. And in this paper, they presented both of them. What's a successful refract and what's an unsuccessful refract. For instance, in this case, the original OIP is close to 1090, and OIP after refract is only minimally changed. So we are not paying that big boxes to do the refract, and we get this much accelerated reserve. So this is basically more details is presented here. So, but at least one of the key messages here is relying on the only 15 days after the refract gives us some ideas about if we have been successful. So we don't need to wait for years to see to classify it as a successful versus unsuccessful. You may argue, well, why don't we use the decline curve analysis? With the decline curve analysis, yes, you're welcome to do that, but for the decline curve analysis, to have a reliable trend of the data so you can fit your lines, it takes a little bit of more information than 15 days to be able to attain that, right? And there are some summary of 29 refract, etc. So you are welcome to take a look at the papers. And in summary, okay, this is the summary of the paper. In the third example, we're going to walk you through the third example here, and then we have another 10 minutes break before we hit the exercise. So it's a multi-phase FMB on the group of. So let's start with the synthetic case. This is so how we treat a bunch of wells for our FMB because we know that they are interacting, they are stealing reserve from each other. There could be some surface communication between the wellbore. In this case, if you have an infill, this is one of the related to one of the questions in the chat. So if you have infill, how we do the analysis? A simple analysis would be, okay, it's a synthetic example by the author of the paper. So it's an infill, and we put the other infill wells on production. This is how cumulative we got here. And talk about the density distribution. So the point of this slide is basically the infill, the parent well, effectively drain its drainage area, but because of low permeability, it doesn't go beyond that. Now it justified that we have the infill to effectively drain this area as well. So there's basically two ways that we can account for a parent and a wellbore. First one is to do the analysis of the individual well and then sum them up. It's very straightforward and it doesn't require any other extra steps to go. And so it's the parent well. We do the analysis on FMB and sum them up. It is 12.4 million reservoir barrel. With respect to analyze, only 3% off, which is quite impressive. The second alternative is to create a pseudo wall. And I'm going to show you quickly how to create a pseudo wall in Whitson. So if you go to walls, and imagine a couple of these walls are draining from the same tank. So we can select them and click on the create pseudo. How does it work? So let's see the pseudo wall. It's simply sum the rates, which makes sense. For the bottom hole pressure, they found that if they do mass weighted average of bottom hole pressure, seems to work better. So for the same synthetic data, they did the same, and they come up with a 12.1 million barrel of the oil in place, which is only 5% within the engineering error. So both of these methods seems to be working fine. While for the alternative one, which we treat each of these valves individually, so you need to run FME for all of them and sum them up. So this is an example for to create the pseudo wall. Yeah, and it's a Permian example. So again, this paper for the group of well, make sure you will get a copy of this paper as well. They did this for a bunch of wells and they analyzed as an alternative tool for pseudo wall, and the results are very consistent. Example 4, I leave it for after break. So you're welcome to 10 minutes break and then we have half an hour to cover the rest of the stuff, which is very straightforward. And we already had those synthetic examples. And then we're gonna take a look at the example that we provide for the course. It should be very straightforward. So wouldn't take more than 15 minutes to walk through those examples. Please enjoy your break time and we'll see you in 10 minutes. If you have any question, please send it in the chat box. I will address them while we get back from the break time. All good. Hope everybody enjoyed their break and there's a couple of questions here. First one is for gas condensate with CGR in the range of 10 to 60, which is classified as a lean gas condensate. What would be the recommendation? Single phase or multi-phase? Definitely FMB. Some multi-phase version of FMB, because even with this small amount of the condensate may have some impact, but I'm gonna show you one for the dry gas, and then you can generate some example for lean gas condensate and see how would the result would be different between single phase FMB and multi-phase FMB. How long should we wait before doing the analysis post cleanout? So we need to wait until we get a kind of a stable trend line on the data. So that would be my recommendation. That definitely depends how quickly we are flowing back the balls, right? If we are flowing back the balls slowly, or if you are flowing the back aggressively, so the impact of initial disturbance that due to hydraulic fracturing operation and completion, the amount of water that we put in the wellbore, if we get rid of those disturbance quickly, then the line should show up more quicker. We could also use FMB to check OIP before and after bracket. Yes, exactly. That's one of the examples that I presented. The paper will be sent out quickly after the meeting, maybe tomorrow or today or tomorrow. So there's another version of FMB, which is based on the dry gas FMB, and I'm gonna quickly show you. This is, you can access this from dry gas FMB. So I'm gonna quickly make a case for you. And this is, you're welcome to join me to follow the steps. I'm gonna call it dry gas, dry gas. And the dry gas, the only difference would be the fluid properties, right? So the method of initialization of PVT instead of GOR would be dry gas. And we need to specify gas at specific gravity, in this case 65, and save it. And PVT is initialized. See, the phase envelope is very minimal, small, but we are operating at this pressure and temperature, so we won't be able to heat this phase envelope. So we're gonna stay single phase in the reservoir. So we're going to the numerical model, and again, to make sure that we drain from this tank in 1,000 days with depletion. Click on this one and click save and simply run the model. And if you run the model, it's going to be my production profile, export, synthetic, yes. And then this is 10 BCF and in the flowing material balance, click run. It's a pretty straight line. You see when the data is not disturbed by a sudden change of the compressibility of single phase to multi-phase transition, it's present itself much cleaner. So if I go to the edge of this and grab this data, so already the data is on a straight line, so indicating the boundary dominated flow has happened much early in the life of the well. So spray on, select this data, and the is 10 BCF, right? What I inputted there. So 10 BCF. And then for this dry gas, there's another option, which is called simply for dry gas. It's a kind of iterative approach. So this is, you see, there's no iterative approach. If you switch to flow material balance type gas, then I'm gonna input my OGIP, which is 10 BCF, and my line is lining up on the data. So why it is iterative approach? So you can see if I adjust the slope of my line, look at the data will dance as well. So what the data is telling me, the line and the data are not aligned, so I have to make them align. So I try to put them on the data, then the data show another slope. I have to do it multiple times before I settle on, which is if I adjust my line anymore, a minimal change, right? This is why we call it iterative. And let's settle on 10 BCF that we simulated. So one more example here. So this was about okay, somebody asked about the fracate. So this is the fracate example. So the beauty of this example is so this is from the SPE repository dataset. So you have access to the dataset. You can try this exercise by yourself. And the pore volume reduction after fracate, it's the fracate that still cause some damage to the parent well. And when we do the flowing material balance, we realize that pre and post fracking, we almost lost 30% of the reserve from 30 BCF to 19 BCF from the flowing material balance. And this same data set has been investigated by three legends in the area. With a multi-phase FMB, it's a 36 to 37% loss of the reserve. And these two gentlemen also used totally different approach. It's rather than the flowing material balance. This is dynamic fluid in place calculation and fractional RTA. Each of these papers by itself investigated the same data set using different approach, but it's very interesting to see all of them settled on the same reduction of the fracate. So this is pretty much the end of the slides here. But now you're already familiar with the software, but I want to walk you through some of the examples that we have in the next while. If you go to those, please, these are the synthetic examples that we went through. And if you click on the mass upload, and go to the example section, you see in the example section, mass upload, example section, and RTA certificate. There's a 3-well in this example. Upload, click on upload, and the data should show up here. I refresh it. Okay, didn't happen. I'm gonna try it one more time. Mass upload, example, RTA certificate, upload. Question is, could I use multi-phase FMB for dry gas production, or should I use only gas? So as you see, both of the methods yield the same result. So I'm going to show it one more time. So once you upload the example, it's going to be the 3 data set that we're going to take a look at. So one of these wells is actually Pheasant well, is a dry gas reservoir. Let's take a look at that. So if you click on the Pheasant well, so in the well, once you uploaded the example, 3 example, one of them is Pheasant. You click on the Pheasant well. These are some of the information. These are from the SPE repository data set. So it's a great data set. This is the same data set. Not the same data set that the authors use for their analysis and testing their methods. So if we go to fluid material balance, first thing first, we need to initialize PVT. So if we go to the PVT, please, and click on the edit and change the method of initialization. It is defaulted by GOR. Now change it to dry gas and make the gas specific gravity 65 and click on save, and this generate my PVT. Now go to fluid material balance and simply click on run. And if you click on run, you see how nice data are presenting themselves. And we can clearly see that this is my straight line portion of the data which present boundary dominated flow. And if I do so, I end up to, if I do the calculation for the bottom hole pressure calculation, so I end up to 20 BCF in place volume. And quality check of the data, yes, average pressure is higher than bottom hole pressure. There's no build-up data, so I can compare those. Water saturation stayed relatively the same. It didn't change much. And so it's pass all the quality tests here. So keep this in mind, 2021 BCF. Now switch to gas FMB. As we said, this is an iterative approach. So what I'm gonna do, I can simply make it 20 BCF, 20 BCF. I'm almost there. Now I have to adjust my line a little bit, maybe make it a little bit, and the data stay almost on the same line. So 21 versus multiphase, which gives me almost 21 as well, right? So multiphase is very generic, general approach. Dry gas is iterative, and also it's only apply for the dry gas. It doesn't account for the multiphase. So always start with the multiphase, and always start with multiphase and confirm it with the dry gas. All good. So this is the dry gas. Very simple. Now you see how quickly I'm running through this. And let's go to another valve, which is the kite valve. I'm going to show you something interesting here, which is basically comparing the result from FMB with respect to PNR decline, right? So if you switch to the kite valve, and so kite valve, and go to the PVT, again, the same step. I have to initialize my my PVT here, click it on save, and my PVT is initialized. Take a look at that. It's undersaturated. This is the bubble point. So when my bubble point pressure is hit, when the bottom hole pressure go beneath, underneath the bubble point pressure, I'm expecting my data to take on a totally different slope, which I simply know what's the reason for that. So go to fluid material balance section and click on run, and let's see what we can get out of these. So, well, how do you would you analyze? Where do you pick your slope, right? First of all, we take a look at bottom hole pressure. We clearly see that this is not acceptable because some of the bottom hole pressure is above this, the average reservoir pressure. So we're going to focus on the early time data before we see the saturation pressure. Select this data, break on them, and I'm going to select this data, excuse me, and then run the calculation to calculate average reservoir pressure. And now it is passing the sniff test, right? All of the bottom hole pressure is below saturation pressure. Sorry, my voice is gone now. And but for the saturation, water saturation, I can clearly see that it's drastically dropping. Maybe I need to question what's the initial water saturation. In this case, it's initialized with 32%, but you're welcome to challenge it, bump it up, and do your analysis. But remember, if you adjust this volumetric, the petrophysical properties, it will impact your pore volume contacted, and that has direct impact on the field development, because you're gonna, where do you want to place your next well? If this well is effectively draining this much, where do you want to place your next well? So I'm happy with this one. My OIP is a little bit shy of 800,000 STB. And now I'm gonna do a complementary part of these, which is the recovery factor calculation. So let's see what we have here. So recovery factor shows a clear trend here. I'm gonna zoom, so I'm gonna grab and move horizontally. So to lock in the zoom functionality here, then I'm gonna lock it. Now is the checklist I have to accomplish here. For my checklist, I have already run material balance. That's the result shown on this plot here. The second part, I'm gonna add some data point, right? At OGR, I'm gonna add some data point here, starting from here and adding some data point. I can use my analog information. It's gonna be my prediction. I have a guideline, which is this 1 hour RV curve. You see how it is shaping, curving upward. So I'm gonna follow similar trajectory. You're welcome to adjust this one and see, okay, maybe I need to put it here. This is more representative. So another check mark here on the OGR. Now the third part here, it is water gas ratio. And therefore, I'm gonna do this one as well. And steadily over here. And then once all the steps are completed, now click on run. What I'm expected to see from here is a recovery factor plus and its corresponding EUR, right? 151, 154. You may you may question, well, 154, it definitely depends on what number I have selected for this profile. So if I adjust my profile for the OGR and water gas ratio, definitely really impact the analysis that I have done, right? So let's feel comfortable with this one. Maybe argue that, okay, maybe a little bit lower to see the impact of that. And you can see I can adjust it on the fly. Now I have added another line, another data point, which is unnecessary. Can grab it, put it here. This one is redundant. I can simply take it and throw it out. Then the line gets connected easily. So let's run it one more time. 151 is dropped to 136, right? Because I drastically drop it here. And then I can take a look at the OGR versus oil. So this is a profile. This is my trajectory. So if you think this is believable trajectory based on your analog wells, then feel comfortable to move on to the next step. So there's another functionality here, which is the PNR DCA. PNR DCA not only account, it's the advanced version of DCA, which also account for the bottom hole pressure. I'm gonna do the same practice because it's also estimate EUR, right? It estimate the EUR, and I'm gonna see right without doing any analysis, only the curve fitting, utilizing readily available production data on the surface, as well as bottom hole pressure, either calculated or from the gauge, what would be EUR. So as in terms of the functionality of the plots, very similar to the rest of the software, and make it consistent. So I'm gonna go ahead and you can adjust the size of the circle by simply your middle mouse button, and then we can grab a bunch of data here. Let's see what I'm predicting on my EUR. And this is predicted to be 190, right? And I'm sure in the fluid material balance here, what we are predicting on the recovery factor is 136. Let's adjust this curve a little bit to our favor. Well, by that, I mean we can adjust it, bump up this profile a little bit here, and maybe this is the better representative of the profile, and then rerun the calculation. Is 136. I'm expecting that to go up, but there could be other factor in place as well, because not only change for the oil, but also it will change for the gas. So 170, right? Is not contrary, is aligned with our expectation. So 170 here, simply material balance calculation. No fancy of grading of numerical simulation, etc., etc. And so this is 160, 170 with a PNR decline. What I'm getting at is 170, right? Well, I can adjust it. Well, I don't want to torture this data, because if I torture it so much, you're going to confess that, well, we are identical. And then you will be under the impression that all of these methods should give you the same result. While this is curve fitting simply, FMB is physically constrained. That's the more reliable, analysis to rely on. So there's another valve here. For the time being, I quickly show you that, but it's very identical to other walls. The PVT, it's PVT adjusted the initialize GOR and initialized by PVT. And yeah, once we do that, we go to fluid material balance, run it. So once you started to see many of these examples, you start to feel confident and comfortable that what would be the typical shape of the data that I'm expecting, right? So in this case, this is the entire history. The beauty of this data set is that we have a build-up data. So let's work through our workflow and focus on the early time data because that's present in the shallowest slope. I'm gonna go spray on this one and select this data and run it. And then I wanna make my analysis in such a way that because I believe my bottom hole pressure data, therefore I'm gonna enforce my slope. So bottom hole pressure calculated be touching the top of the bottom hole pressure here. So I can either disregard the data and the slope they are presenting themselves because I know I'm hitting the saturation pressure. In order to confirm that, let's do one highlighting practice here. Lasso highlight and lasso this part here and see the bottom hole pressure. It is close to 22 100 pound. The PVT section in the PVT table is 23 2400. Very consistent, right? So I know those data, those slope are not trustworthy. So I don't put much weight on this part of the data. I look for the shallower slope. It seems to be the shallower slope, shallowest slope. But the fact that they will only produce for 300 days, right? Not much, 350 days. Maybe I haven't explored all area. I need to take a look at the data. If it is in, for instance, in the Eagleford, the permeability is 50 nanodarcy. I'm not expecting to reach all the boundaries within 350 days or other information if it is a parent well, if it is infill well, if it is bounded, unbounded well. So if it is unbounded well, I'm expecting it take much longer to explore all the boundaries because it's unbounded simply. If it is bounded well, I know I'm constrained, physically constrained in terms of the drainage area because other offset well is also competing for the reserve. So I'm going to be dealing with some certain volume that's match my volumetric based on the valley spacing, etc., etc. But in this case, I have a good chunk of build-up data that I'm going to trust. So I'm going to adjust my line, if you allow me to, and we run it one more time. And sorry, I have to run it one more time. If it doesn't work, please refresh because a lot of people working on the same project, so it doesn't show. It's need a little bit of help to refresh itself. So it is not working. Now it's still, so maybe I need to still adjust my line a little bit more there. So you see now I'm feeling comfortable that I'm honoring my build-up. This is basically flush production. So we can safely ignore this, but as they I am honoring this one. So this is minimum reserve that I so far I have been exploring. The well has been exploring, and if I let it produce for a little bit longer, the data will show up and align themselves along this line. So for the whatever left to our meeting, 10 minutes, 8 minutes. If you have any question, please. This is basically the end of the exercises as well as the slides. So hopefully you enjoy the course. Hopefully you learn something. What we owe you is the recording of the course as well as a couple of papers. I thank my colleagues, Anna, Felix, and Sri, helping out addressing the questions. If there's an outstanding question, please reach out. We will be happy to dedicate some sessions with you as a follow-up and help you appreciate the FMB. Or if you have any other outstanding question, please let us know. Other than that, wish you great rest of your day. And it was my pleasure to have the opportunity to get to know you. And please provide any feedback that you might have. It's definitely help us to fine tune, gauge, and include some of the information more actually material. Well, you can imagine in 3 hours time, I try my best to deliver the gist of the message here. I hope you enjoyed.